Hi everybody. What we're going to talk about right now is the force on an electric current in a magnetic field. You learn from your conceptual videos that moving charges create magnetic fields. What also happens is moving charges experience a force when in a magnetic field. If those charges are in a wire moving together as a current, there will be a force on those charges and therefore on the entire wire. This is governed by a very, very simple formula that says that the amount of force that you get depends on the current and the length of the conductor, the magnetic field, and the angle between them. Okay, so for instance, if I had a magnetic field moving like this, and I had a wire in that magnetic field, and let's say the angle between them is 60 degrees, there will be a force acting on that wire that depends on, again, the current, the length of the wire, the size of the magnetic field, and that angle. Let's do a quick example of that. Let's say that the length of the wire is 12 centimeters, which we know is 0.12 meters. Let's say the current is 30 amperes. And finally, let's say that the size of the magnetic field, is 0.90 Tesla. All we'd have to do is put those numbers together and multiply them along with the sine of that angle, 60 degrees, and we would get the size of the force. So the force would be the current, 30 amps, times the length of 0.12 meters, times the magnetic field strength, 0.90 Tesla, times the sine of 60 degrees. That would come out to 2.8 newtons. Now, what you could probably see, if you look at this, if the sine is 0, you're going to get no force. In other words, if this wire was perfectly parallel to the lines and crossed none of them, you'd have no force. So in order to actually have a magnetic force, the wire or the motion of the charges has to cross the magnetic field lines. You get your maximum force when they're perfectly perpendicular to those lines. The challenge to this can be finding the direction of the force. The way we're going to do that is use something called a right-hand rule. The right-hand rules are necessary for a lot of this magnetism stuff because the multiplication that's involved is vector multiplication called a cross product, which gives you some funny results compared to things we've done in the past. And without getting too mathy on you, but a right-hand rule involves, now this is going to be awful, but I'm going to do it anyways. Here's your thumb. Okay, yeah, that's the world's worst looking hand. I get it. If you create this shape with your hand, your thumb represents the direction of charge motion. So your thumb would be the current. The many fingers would represent the field lines. Your palm, if you imagine that this is my palm laid flat on the screen, is facing into the screen. The palm is the direction of the force. So what you have to do is you have to line up your thumb with the current, line up your fingers with the magnetic field, and your palm will actually point in the direction of the force. So in the case of this over here, this is actually how it's already kind of lined up. My fingers are pointing to the right, my thumb is pointing up, more or less, and my palm would be facing into the page, which means that this force would be 2.8 newtons into the page. One really helpful hint about this is that you have to use up all three dimensions when you work with this stuff. So in other words, if the B field is left to right and the current is in the top to bottom dimension, then the third dimension, which would be in and out of the page, has to be the force. So you can never have a force that is in the same on the same axis as the current or the B field, if that makes sense. Hopefully it makes sense. If you have issues with this right-hand rule stuff, see me in class, and sometimes it's just easier to see with somebody standing in front of you.